probably wasn't. But he was but we have a relationship with him. And we learned it when we established that.
Hi, Drew. I think there's no one here to introduce you this time. I don't see anyone. So
That's
you
all
may
right.
have to introduce yourself this time.
I just got the Zoom link, so
Uh,
okay. Well, thank you all for coming. I've given a few talks to you guys, so I recognize a couple of faces here. So I'm meteorologist Drew Montreuil from Finger Lakes Weather. In the past, I've talked about a variety of things. I think the last talk I gave was on the severe thunderstorms and tornadoes in 1998. I think that was about a year ago that I gave that, and I did not envision that I would be making a new talk on the severe thunderstorms and tornadoes in 2024 when I gave that, but here we are. So I'm going to get my screen going, and we're going to talk about what we had going on last year. It was a record tornado season, but I've got a little asterisk there, and I will explain why I put that there as we get towards the end of the presentation. Um, just real quick, since I didn't get in here ahead of time, can everybody hear me okay and everything good?
yes.
Okay, great. All right, so let's get into it. So the first part of this talk is going to be very similar to the talk I gave on the thunderstorms in 1998. Um, I took out a couple of those slides that I went over last time, so I don't have to go as deeply into it. But for anybody who wasn't there that time, and also just for a refresher, I'm going to go into what makes thunderstorms, what makes thunderstorms severe, and what we know about how tornadoes form. I'm going to briefly go over how um, the risk of these thunderstorms is portrayed out to the public through outlooks and watches and warnings. I'll go over a little bit of New York State's tornado climatology, and then we'll talk about some of the tornadoes that we saw last year and how it all fits into New York State's history with tornadoes. So without further ado, thunderstorms 101. Um, for a thunderstorm, you need three ingredients. It kind of all boils down to that. You need some moisture in the atmosphere, you need a sort instability in the atmosphere, and the instability is what fuels the thunderstorm growth. And you need something to trigger it all, get it all going. And then the fourth ingredient is the wind shear, and that's what takes a normal thunderstorm and turns it into something more powerful. Um, a lot of times in our region, we don't have high levels of all four of these things. You know, that's something that you see in Texas or Kansas or down in the South where everything comes together and you get them big, massive tornadoes and big, massive outbreaks. Thankfully, we don't usually have that here. But as we saw, especially this past summer, even if just one or two of those things is high, it can offset the others not being quite as much of a factor. Um, that's why our events are a bit harder to predict in some ways, and why they don't happen as often, thankfully. So moisture, it all kind of starts there. We need moisture because that's going to help support the cloud growth. Dew point is something you'll hear on the news, something I talk about a lot. That's a measure of the moisture in the air. It basically, if you cool the air down to the dew point, you're going to get the water vapor condensing into a cloud. As the warm air from the surface during the summertime rises, it cools and eventually it reaches that dew point and condenses into a cloud. So what happens then, depending on how much growth potential there is for that cloud, that's where the instability comes in. So as the moist air cools, um, it's actually going to cool at a slower rate than air that would be dry. So um, that imbalance is what we call instability. So if we imagine here in this little box, we have a bubble of air, we call it a parcel. And this is kind of a hypothetical thing. It doesn't quite happen exactly like this, but this is the best way to take this kind of abstract idea and understand it. So we take this bubble of 80-degree air and something makes it rise. Okay. That bubble of air rises. It's still 80 degrees, but the air around it now maybe is 60. So that's an imbalance. Warm air being less dense, it wants to rise, and so it kind of starts to take off and it goes faster. It does start to cool, but because it's moist air, it's not going to cool as quickly. So in this case, it's down to 50, but the air around it is 32 degrees. And as it starts that quick upward motion, that's when we start to see the cloud growth. If you've ever watched one of those thunderheads in the summer, if you just kind of stare at part of it for a few minutes, you can just see it growing and expanding. And that's the instability that we're seeing. So we get our cloud growing, it grows fast. Eventually it hits kind of a top layer of the atmosphere and it flattens out into that anvil shape. Um, that intense upward motion causes static electricity basically, and that's where we get the lightning. It can take pieces of ice and move them up and down in the storm and it gets bigger and bigger, and that's hail. So there's a lot of stuff going on. Technically, we call all this instability convective available potential energy, or just CAPE. Values of CAPE under 500, you might get a little bit of lightning, but not usually a big storm. Over 1,000 is that's you're getting pretty favorable, especially around here for strong thunderstorms. And if you get over 2,000, then that's a very robust atmosphere that's very much primed for severe weather if everything else is there as well. Triggers, one of the most important parts of all this. You can have all the instability in the world, you can have all the wind shear in the world, you can have all the moisture in the world, but there's nothing to get the system going. If there's nothing to give that parcel of air that initial nudge upwards, then not much is going to happen. Some different examples of triggers: cold fronts, warm fronts, a lake breeze. We can definitely experience that in the summer off of Lake Ontario or Lake Erie. It acts as like a mini cold front in the afternoon, can trigger thunderstorms. Thunderstorms can also trigger other thunderstorms by the cold air that blows out ahead of them, and that's called an outflow boundary, and that can pop up new thunderstorms as well. The stronger a trigger we have, the more widespread the thunderstorm activity is generally going to be. So those are the three basic ingredients, and then the fourth piece that takes it from its normal thunderstorm into something that is threatening is the wind shear. And wind shear is a term that gets thrown around a lot by people anytime there's a lot of wind. But the more technical definition is wind shear is different wind speeds and or directions at different heights. So in this picture here, we have strong winds up at the thunderstorm cloud level. That's represented by the thick arrow. And we got weaker winds down towards the surface. Even though the winds are weak at the surface, that doesn't matter as much as the fact as that there's a big difference there. Before I go to that one, if you imagine sticking like a pinwheel in there, you can imagine it turning because of that stronger wind up top. So what this helps to do is, if the winds are all the same, thunderstorms go through a pretty quick cycle of bringing in warm air, causing it to rain, and then the cold air, that rain-cooled air, cuts off the warm air and the thunderstorm falls apart and dies. Sometimes that can happen as quickly as an hour or so. What the wind shear does is it helps the warm updraft and the cold downdraft coexist, so that the cold air isn't cutting off the warm air, the warm air is not cutting off the cold air, and it works like an engine and it just keeps going. So that gives the storms more time to organize together and strengthen. Like I was saying, the wind shear causes a spin in the atmosphere. So in this example, we've got wind coming in two different directions. So the little bullseye icon is like an arrowhead pointing right at you. So the wind's coming right at you. And then down at the surface, the wind's going a different direction. So that's going to cause this little bit of spin. Again, if you imagine some sort of a pinwheel or wheel in there, or like a marble, that marble is going to spin in there because of the differences. And if that spin gets caught up in the updraft, it goes from spinning vertically to getting turned and spinning horizontally. And sometimes, not all the time, but sometimes that leads to a tornado. Now, why some storms that are spinning horizontally like this produce a tornado and other ones don't, that's one of the big mysteries we still have in meteorology. So there's still a lot to learn about how tornadoes form and why some storms produce them and why other ones don't. There's a couple of main types of storms that produce tornadoes. There's the more classical supercell. Usually these are individual cells that are kind of discrete by themselves. They often have kind of a hook shape. Let's see if I can get a laser pointer on here. So yeah, so they've got this hook shape, and right here where it curls in on itself, that's where the strong rotation is, and the possible tornado. They are the main producers of tornadoes when you look at like the country or the world as a whole. Not so much the case here, as we'll see. They can also produce very, very large hail, extreme winds, the whole gamut. So these are the things that the storm chasers like to chase out in the Great Plains because they can position themselves to the south of the supercell, and there's nothing really obstructing their vision of where the tornado is on the southwest side. And the storm is usually moving away from them, so they're also safe. More common around here are bow echoes, and they don't always produce tornadoes. That's not usually their main threat. Usually they're more like a squall line, and widespread damaging winds are their primary concern. Um, but especially at the top and the bottom of the bow echoes, we get these shears that can spin up tornadoes, and we'll see a really good example of that later on. But also within the line itself, just as different parts of the line move ahead faster than the nearby parts, that can also create spin ups and tornadoes. And a lot of our tornadoes actually come from this sort of a setup here. There is also a technical term called derecho. That's when we get these massive bow echoes that span hundreds of miles and last hours or even sometimes overnight into the next day. Bow echoes can also produce hail and, of course, tornadoes, but damaging winds are usually more widespread than those other things with a bow echo. Okay, so how do meteorologists let everybody know these things are coming? Um, it's very difficult actually to really capture a given situation and communicate that to the public, partially because severe thunderstorms tend to be so isolated. You know, one part of town might get absolutely hammered, and then a mile down the road, it's fine. Um, so communicating that risk and balancing it with not underestimating the potential of the thunderstorms, but also not making it sound like everybody's going to lose their roof on a given day. It's a very fine, delicate balancing act. Um, Nationally, the Storm Prediction Center is in charge of predicting severe thunderstorms. They are part of the National Weather Service. They are located in Norman, Oklahoma. Um, I always find it ironic when they have to take shelter because they've got a tornadic supercell coming right at them. But you know, they like being right in the middle of the action. So they issue outlooks every day, multiple times a day. They have 5 general categories of severe weather. I'll talk about those in just a second. They also issue the severe thunderstorm and tornado watches. They work with the local branches of the National Weather Service to do that, but they don't issue the warnings. That's fully on the local offices. So for our area, the Weather Service office in Binghamton is the one that's going to issue a severe thunderstorm or tornado warning. They'll communicate with the Storm Prediction Center, and the Storm Prediction Center will issue a watch, but not the warnings. The Storm Prediction Center also does a ton of research, so they're really helping to advance the science of severe thunderstorms as well. If you go on their homepage and just scroll down a little bit, they've got a big list that they're constantly updating of the latest journal articles they're publishing and a whole variety of meteorological bulletins. So here are their categories. They have just a general thunderstorm category where there's generally not severe weather expected. Then it goes to a marginal risk. We see quite a few marginal risk days every year. that's when you might get a thunderstorm that'll briefly become severe for a little bit, but generally most areas aren't going to see very much at all. Most of the outlooks we get when there's actually severe weather going on, more than just an isolated thing, is a slight risk. Um, that's kind of an isolated to scattered severe thunderstorms. Some of them could pack quite a punch, though. Um, Enhanced, we usually see maybe once or twice a year. That usually means that there's quite a few severe thunderstorms around, pretty high confidence. Some of those could be particularly strong. A moderate risk, we probably see once every 5 years or so. That's usually a pretty widespread event. And then the high risk has only happened once here, and I talked about that last time. That was on May 31st, 1998. And that is usually something you only see in the whole United States a few times a year. So that's really reserved for the really biggest, worst outbreaks of severe weather. So hopefully we won't see that ever again. So watches and warnings. Watches means conditions are favorable for a given weather, in this case severe thunderstorms or tornadoes. They're in effect over a very large area spanning many counties and usually several states. And they're in effect for a long period of time, usually at least 6 hours, sometimes as much as 12 hours. And that's kind of your first heads up that the Storm Prediction Center is watching your area for some sort of severe weather. Doesn't mean it's happening yet. Doesn't even mean it's necessarily going to happen in your area, um, but you need to watch out. Now, a warning is more serious. That means that the hazardous weather condition is occurring. This morning we had snow squall warnings because there was an intense snow squall moving through. There wasn't any question about it, it was there. So they're issued over a very small area, especially the tornado warnings. They really try to narrow it down to the area um, that is going to be most likely impacted by a potential tornado. And they usually have a short time of 30 to maybe 90 minutes. So here's an example from 2022 where we have a tornado watch over most of upstate New York. Back to the southwest, they have a severe thunderstorm watch. And then they got some smaller severe thunderstorm warnings addressing the individual thunderstorm cells. So the whole area is under a tornado watch, even though the storms aren't even in to the watch area yet. It's just that kind of heads up that as these storms move in, they could turn tornadic. And if all that doesn't make sense, you can just think of tacos. This is one of my favorite slides to always show people. Um, if all the ingredients are in place on the table, you've got a taco watch. There's a possibility that you'll get a taco out of all this, but you don't have a taco yet. And if you have a taco warning, there's your taco on your plate, ready for you to, in this case, enjoy. Okay, so let's talk about tornadoes in New York now. This has long been a very interesting area for me. It probably goes back to that 1998 event when I was a kid, when we had all these tornadoes, and it was like, wow, tornadoes happen in New York. And so I've always been very interested in researching it, and I've got this big database saved on my computer and everything. So records for tornadoes across the whole country, including here in New York, date back to 1950. Um, the records back then are very sparse. It was almost taboo to even say tornado as a meteorologist back in like the 50s and everything. And so they weren't very often reported or even known about. As technology and awareness has increased, so has the number of tornadoes that we've found. So between 1950 and 2020, there were 452 tornadoes officially recorded in New York, probably many more, but that's what is in the database. And thankfully, 82% of those, so very, very large majority, are weak. So that would be an F0 or an F1 tornado. And I'll tell you what that actually means in just a second here. So here's a map I made of those 1950 to 2020 tornadoes, and the color coding shows where they are most likely to happen based on just a simple density algorithm. And it's very highly correlated to geography across our region. The Hudson Valley, Mohawk Valley, Those large valleys act to funnel the airflow at the surface, and that creates a little bit of extra shear in the environment that can produce tornadoes. Similar thing happens off of Lake Erie and a little bit to the southeast of Lake Ontario with those lake breezes. And then even some of the broader valleys in the southern tier show up as a little bit of a hot spot for tornadoes. And then very sparse tornadic activity up in the Adirondacks and North Country. So here is the rating scales. Now, when you're doing tornado research and talking about past tornadoes, um, depending on what year we're looking at, it's going to depend on which scale we use. So up through 2006, we used the Fujita scale, and in 2007, they revised that into the enhanced Fujita scale. And that actually causes some issues when we're talking about comparing today's tornadoes to earlier tornadoes. And I especially talked about that in the 1998 event because it's especially prevalent here in the middle of the scale. So on the old scale, an F2 had winds anywhere from 113 to 157 miles an hour. So now that in modern terms covers an F2 or an F3. An F3, or sorry, an EF2 or an EF3. An old F3 goes all the way up to 206 miles an hour, which actually even eclipses the EF4 stage into EF5. So a storm that used to be a 3 could now be classified as a 5. And that's a pretty big difference in just the public perception of how tornadoes are evolving and everything. So that's just a little important thing to keep in mind that the scales are different. It's not just a adding of the letter E in front of it. It's actually fairly significant difference, especially in the middle. Okay, so now we got all that taken care of. Let's dive into a little bit of what we saw this past year. So here is the still preliminary. None of this data has been like officially officialized yet. It usually takes about a year for the Weather Service to do their research and go back and look through things. So everything is still considered preliminary at this point. But what they've got right now is 32 reported tornadoes in New York State last year, all represented by these little red triangles. All of them are in upstate New York. You could make an argument that that guy's not upstate, but everybody else, all these other tornadoes are definitely northern, central, and western New York. These two bigger triangles are strong tornadoes with a EF2 rating, almost EF3 on one of them. So I wondered how that corresponded to our climatology and so I was able to overlay those data points with the map I showed earlier. And not too surprising, lots of them near Lake Erie, lots of them kind of in central New York, this hot spot. Quite a few surprising ones getting into that kind of lesser area of the Adirondacks and North Country, which has given me an interesting hypothesis that I'll mention later. And then, just a couple other scattered ones throughout the region. So not too many surprises with that. A little bit of a surprise here in the southern Adirondacks, but not too much of a surprise. So like I said, in all, there were 32 tornadoes recorded in New York. They were spread across 11 different days of the year. That was led by July 16th, when there were 10 tornadoes. July 10th had 7 tornadoes, and July 15th had 4 tornadoes. So that's 21 of the 32 tornadoes in a span of 6 days. An interesting note about the tornadoes on the 10th is they were actually associated with the remains of Hurricane Beryl. When hurricanes come inland, because there's such a tightly compacted spinning storm, there's a lot of wind shear with those storms. And like I said, we don't fully understand how tornadoes form, so sometimes those inland remnants of hurricanes produce lots of tornadoes, sometimes they don't. In this case, Beryl did, and we were kind of got some of the brunt of that. The earliest tornado, believe it or not, was on February 28th. That was down near Binghamton. The latest was on September 9th. That's probably pretty typical for a latest tornado on a given year. Usually there's a tornado or two in early September, so not too surprising there. So compared to other years, the previous record was in 1992 when there were 25 tornadoes. 2011 and 1998 had 23 tornadoes each. 2003 and 1989 had 18. So we've had big tornado years before, but this year really kind of took the cake. As I said, based on the map, there were two strong tornadoes, and unfortunately, there was one fatality from one of the tornadoes. But otherwise, I'm not aware of any other injuries from any of these tornadoes. So I'd like to point out a couple of these notable tornadoes that are particularly interesting. We'll start with the one that was on February 28th. As surprised as I was to see that there was a tornado in February, and I remember looking this up right when it happened. It's actually not the earliest tornado that we've had in New York State's history. There was one on February 24th, 1975 in southwestern New York. This was a pretty typical sort of tornado that we see here in New York State. Wasn't on the ground very long, less than a mile, not very wide, about a football field and a half. Maximum winds were about 100 miles an hour, and this tornado did come out of a squall line. So it was kind of that bow echo type tornado, not a supercell. Not a discrete individual supercell. Okay, the next one that was interesting was on July 15th, not far from us in Virgil. This one happened at 6:30 in the evening. It was thankfully weak, just an EF0 with 80-mile-an-hour winds, but it was on the ground intermittently for about 7.5 miles. The Weather Service in their report said it was inconclusive if it was on the ground the whole time because it kind of went skipping through the hills. So it may have not been directly connected to the ground that whole 7.5 mile path. It was also associated with a squall line, but the really interesting thing about this one is that it crossed paths with a tornado less than a year earlier in August 2023. And the intersection of those two paths was almost right at Greek Peak. So that was very interesting to see here in New York, the same area get two tornadoes less than a year apart. I'm not aware of that ever happening like that before in our state. July 15th. This is Canandaigua, but that picture's wrong. That picture should go with the slide for Rome, which I'll talk about soon. Anyways, July 15th, 4:50 in the afternoon, another very weak short tornado, less than a mile, 75-mile-an-hour winds, not even a full football field in width. Also associated with the squall line. And this hit right on the waterfront in Canandaigua. So a very busy place. There's a big park right at the northern end of Canandaigua Lake, and then a lot of stores and shopping district, but there were no injuries from this, thankfully. And like I said, this picture shouldn't be here. It's not the correct one. July 16th, so the next day in Canastota, just to the east of Syracuse a little bit. You can see from the radar, we've got a split perspective here. So on the left, we are seeing the precipitation associated with this thunderstorm. This is what you usually see if you turn on the news. On the right, we have the winds that the radar is seeing. The green winds are flowing towards the south. I don't remember if I took this radar out of Binghamton or actually, nope, it's the radar up on the Tug Hill. So the green colors are flowing towards the radar, which is to the north over the Tug Hill. The red ones are flowing probably more southeasterly away from the radar. So you can see as that line comes through, the winds shift, and it's hard to see, but occasionally the green color kind of hooks back into the red, and that's where we're getting those little spin ups. But you can see like this radar doesn't there's a lot of bright colors, but it doesn't look terribly threatening. If you've watched a lot of radar, you see this sort of thing a lot, and it doesn't necessarily look like a whole lot. But nonetheless, it did produce a tornado, went right through downtown Canastota. Unfortunately, there was an elderly man who was caught outside at that time, and he was severely injured and eventually succumbed to his injuries. So that's the one fatality that we had this year. Um, it was on the ground for about a mile and a half and about a football field wide. And you can see towards the end of this that the red color really starts to show that bow shape. And at the northern end, you can see that the greens and reds are kind of starting to spiral around each other a little bit. And that's important to note because half an hour later, now the picture's correct, um, that same storm complex hit Rome and produced a tornado that went right through downtown Rome. And this was a very strong tornado by New York standards. 135-mile-an-hour estimated winds. EF3 starts at 136, so it's basically right on the borderline between a 2 and a 3. It was on the ground for a little over 5 miles, 300 yards wide, so it's about 3 football fields. Again, it was associated with that same squall line, and kind of amazingly, for hitting downtown of a place like Rome, there were no injuries, even though, as you can see, the damage was quite significant. There were several buildings that were completely destroyed, including a couple of churches, but thankfully nobody was injured from that. So that's just a very brief selection of a couple of the tornadoes that we saw, mostly weak ones, but a couple of strong ones, and unfortunately one that was deadly. So how do we place all this into context? Is this the sort of thing that should expect more of coming up? Um, is this, how out of the ordinary is this actually? So to start, there's a lot of, like I kind of hinted at earlier, there's a lot of change that's happened since 1950 when we first started officially recording tornadoes up through the present. Um, One of the biggest changes came in 1988 when the current Doppler radar network was instituted. Um, Before that, it was like you see on like the old movies, all the old wartime movies where they got the little green radar screen and they just see a little dot as the enemy plane is coming, and that's basically the radar they were using. It was very, very rough, very undetailed. You just kind of see these blobs moving across the screen that were the thunderstorms. Once we got the Doppler radar network in 1988, we were able to see things like never before. And then there was actually another upgrade to that system in 2011, which allowed us to see the shape and size of particles, not just that there were particles there. And that has really helped with tornado detection as well. Also, just, in our hyper-connected social media, internet-driven world, it's so much easier to be aware of storms and to also report storms. So there's a much bigger potential that the Weather Service is going to hear about a particular storm causing damage. A good example of this is in, I believe it was May 2000, here where I am in Groton. We had a tornado warned storm, and out on one of the rural roads nearby, um, there was a tornado. I'm absolutely convinced of it. It took a barn down, and you could see the spiraling track through the long grass of the farm field, and then it took out a tree. But that's all it did. It was, one of these ones that's on the ground for maybe half a mile, and it's very not wide at all. Um, and the damage, all things considered, was fairly minimal. The barn that it took out was very old. Um, but back in 2000, people weren't walking around with smartphones, and the National Weather Service wasn't as well known as an organization out there. And even the warnings back then were issued for the whole county, not just an individual storm. So even though this storm was up in Groton and had a tornado warning, folks down in Newfield who weren't getting this storm were still under a tornado warning, even though the storm was way up here. Um, so all those factors combined, the National Weather Service never investigated this damage, and that tornado is not in the record books. But I know it did actually happen. So all these things, really are a big factor when we're comparing years. Um, Even with that in mind, there have been 6 other years with at least 15 tornadoes, and the 3 years in yellow had at least 20 tornadoes. 2 of those years, 92 and 93, that's quite a ways back now, definitely before the new upgraded radar came on and before even the internet was, a widespread thing. Um, so I wonder if the tornado seasons of 92 and 93 happened today, how many tornadoes there actually were and how many tornadoes we'd be able to find. So let me give you some examples of some of the things that came out of the Weather Service reports this year um, that helped them identify tornadoes that they wouldn't have been able to identify, even 5, 10 years ago. So this first one up here in Wayne County, witnesses basically could see like a gust of spirally wind moving a couple of cars. That's all it was. Some people caught it on camera because everybody's got a video camera in their pocket now. There was absolutely no tree damage, no property damage. So they couldn't actually rate this tornado because they didn't have anything to go on. So it's in the books as an EF unknown. There's no way they would have known about that tornado if people didn't have their cell phones all the time nowadays. Um, Another one, drone footage was heavily used in determining where the tornado was in the path. So they could fly a drone up there and see, oh yeah, these trees fell in the spiraling sort of pattern. So it must have been a tornado. This one over here on the side, it's a big long one. It talks about a debris ball on the KTYX radar. That's the one up on the Tug Hill. What the debris ball is because of those new radar upgrades we had around 2010 that can show us what the shape and size of the particles are. When a tornado goes through and it kicks up all the debris, these other modes of the radar kind of go crazy because you got long 2x4s and trees and cars and just all different shapes and sizes of things going all different directions. And so it shows up as these bright colors on certain modes of the radar in this ball shape, and it's called a debris ball. And that is very, very helpful for the Weather Service in identifying tornadoes both in real time and after the fact. So they saw this debris ball on the radar, but it was mostly in an area that was inaccessible. It's out in the middle of the state and national forests where there's no roads or anything. So again, they were able to use aerial imagery to map the track of the tornado, which was mostly inaccessible. And again, like that's a tornado they wouldn't have found in the past. And that's why I find it interesting that when I overlaid this year's tornadoes with the climatology map, um, that we were seeing those ones in the southern Adirondacks, which before was an area that saw very, very few tornadoes. It's maybe there have been tornadoes there, but they've just been out where there's nobody there. It's the whole question of if a tree falls in the forest from a tornado, does anybody actually hear it? Does it make any sound? So, um, we've become so much better at identifying these tornadoes and where they are. It's hard to compare past years from different eras with these modern eras. Ultimately, we had 32 tornadoes. We've never recorded 32 tornadoes, so it's a record year. But that important piece of context is something that you have to kind of keep in mind a little bit. Another thing that really hit home for me this year, and has really kind of changed how I view my tornado research is this little exercise here. So we've got two storm events, Storm A, Storm B. Storm A had 75-mile-an-hour winds. Storm B had 95-mile-an-hour winds. Storm A had a damage path of 7/10 of a mile. Storm B had damage path of 1 mile. Damage width 75 yards, 1,000 yards. So it's an imperfect calculation because we're making assumptions that it's a perfect rectangular area that these storms are damaging. But if you give me that assumption, Storm A damaged about 19 acres of land. Storm B damaged about 364. So Storm A was the tornado that struck in Canandaigua that I talked about earlier. Storm B is a microburst that also struck Canandaigua literally about 2 minutes after the tornado went through. So the news was all over the coverage of the tornado because it was winds going like this and tornado, tornado, tornado. It scares everybody. But the damaging winds were a much bigger impact for Canandaigua and actually did a lot more damage. And a lot of the pictures that were up on the news that the news was calling damage from the tornado, once I actually saw the storm surveys from the Weather Service and mapped out where they were, those pictures that they were calling tornado damage were actually damage from the microburst and the straight line winds instead. A even more drastic comparison, we've got storm event A, 80-mile-an-hour winds, 7.5-mile damage length, 175 yards wide for damage area 477 acres. This is the Virgil tornado that I talked about earlier, the one that crossed the path of the other one. Meanwhile, storm event B had 95-mile-an-hour winds, damage length of almost 22 miles, width of almost 7 miles. Just no comparison in the amount of area that was impacted by this stronger storm. 95-mile-an-hour winds over 80. We're like 3 orders of magnitude bigger here, almost 100,000 acres. This was a microburst event that went through Tompkins County in June this past year, especially hit from West Groton down towards Dryden and Virgil again. So just like with the Canandaigua example, I picked storms that overlapped and where they impacted. And the straight line wind event actually had a much bigger impact. Some people were without power for almost a week from this event. And so my kind of point in this exercise is everybody, there's all this attention focused on the tornadoes, and I've always kind of been part of that, with all my research into tornadoes. It's all about the tornadoes and everything. But for us here in upstate New York, especially, the threat from thunderstorms with damaging winds are much, much greater for any given property or any given individual than the threat from a tornado. The chances of getting hit by one of these tornadoes are almost infinitesimally small. Most of these are only a half mile to a mile wide and path length and only like a football field wide. So it's very, very unlikely that anybody's house or car is going to get hit by a tornado. It does happen, of course. And I'm not saying to not take tornado warnings seriously. But the whole media frenzy around tornado and meanwhile severe thunderstorms are just like, another severe thunderstorm warning. Let's go to the windows and take a movie instead of taking shelter. That's kind of really the wrong attitude to take towards thunderstorms in our area. And, that's definitely something that my eyes were open to a bit this past year with these events. So in conclusion, 2024 was record breaking, but we do need to keep in mind that it's very hard to compare modern records to even records a couple of decades ago, let alone 1950. Damaging microbursts have a lot greater potential to impact any given individual or property than a tornado does. Thankfully, the majority of our tornadoes here in New York are weak, short-lived, very small events. But once in a while, 5-10% of the time we do get stronger tornadoes that can be deadly. So it is important to definitely take them seriously as well at the same time. And I think that's why I've always kind of been interested in tornadoes in New York, because there's this kind of perception that they don't happen here. I remember in 2014, there was a tornado in Madison County that tragically killed 3 or 4 people. I can't remember which. But Governor Cuomo came over and investigated the damage afterwards, and he said in his press conference, tornadoes don't happen in New York. And I'm like, yes, yes, they do. Not very often, but they do. And then, just all the advances that we've gotten, both in the science of meteorology and with the tools that we have, and also just society being more connected with communication and smartphones and everything, that's really played a huge role in identifying tornadoes, getting the warning out about tornadoes, getting awareness out about them. Um, so it's definitely a very good thing to have all these tools, because it undoubtedly has saved lives. Quite possibly even here in New York. I go back to that tornado in Rome that hit the middle of downtown with practically EF3 strength, and that definitely could have killed people, as the storm did in Canastota. But thankfully, because of the warnings and just the whole picture of everything, thankfully nobody was injured in that one. So here's some of my sources. The National Weather Service on their website has a whole bunch of past weather event summaries. I've also used several different databases to build my own database of information. And Iowa State University has a lot of great archived bulletins from the National Weather Service. So I was able to go back and look at the statements that they put out as they were doing these storm surveys. Then the Storm Prediction Center has lots of great data as well. So that's what I've got today. Happy to stay and chat for as long as people want, take questions. If you think of something later, it's just drew@flxweather.com. And of course, you can find all my weather forecasts at flxweather.com. So thank you very much.
Thank you so much, Drew. I should put in a plug, as I'm one of your supporters, and I hope other people will consider making a contribution.
Well, thank you so much. It's people like you that let me do what I do. So I definitely appreciate it. Has anybody got any questions or?
Yeah, Drew, I have a question. You mentioned early in your talk, that around in the 1950s, people, you didn't let people know there were tornadoes. It sounded like it was kept hush hush on purpose. What was the reasoning behind that? Or was it just
Yeah,
because you couldn't detect them as easily?
it was mostly because they didn't want to trigger like mass panic.
Mhm.
So they just it was just kind of protocol to not say that because you didn't want people panicking. And I think probably a large factor in that is the fact that it was, you know, next to impossible to predict and detect them back then. There would have been a lot of crying wolf and people not, getting all up in a panic for no reason. Um, so yeah, it was just kind of policy I'm not quite sure when it exactly changed, sometime in the 50s or 60s. Somebody issued the first like tornado forecast and it just kind of all took off from there. Like, oh, people didn't panic completely. So so that's the story that I've read online several times, like in the Storm Prediction Center's history and stuff.
Thank you.
Yep.
Drew, uh, people up north sometimes have shown pictures of water spouts. I wondered if a water spout is really the same as a tornado, only over water, or is there a difference?
Okay, so there's two types of water spouts. There are water spouts that are tornadoes that develop or move over water. So that type of tornado, yes. That type of water spout, yes, is just a tornado over water. The ones that people tend to share on social media, especially in the late summer, early fall, up on Lake Ontario, those are not true tornadoes. They are driven by, again, it's more closely related to lake effect than a true tornado. Now, lake effect is actually the processes are very similar to a thunderstorm with that instability, because you've got the warm lake water with the cold air over top of it, and that gets that upward motion going. And the lakes are very warm in the late summer and early fall, and that's when we first start getting those cold air coming in. So that's kind of when that difference is maximized. And those types of water spouts are very hard to study because they're out over the lake. They tend to be short-lived, and there's not really a good way to collect data on them. But they're definitely a very interesting thing that happens. I did 4 years at Oswego, and finally in my senior year, I was able to see a couple of water spouts over the lake. That was if you literally imagine the entire meteorology department in the middle of class getting up from their seats and running to the lake shore, that's what it was like. But so they're really cool. There is actually once in a great while something similar that happens on Cayuga Lake, and I've got a picture of it that somebody sent me back in 2014 when we had a real cold air outbreak. Let me see if I can get it. It's like that sort of a water spout. Here it is. Out over Cayuga Lake. Just share it here. And make it a bit bigger. And what I think happens, so this is kind of more like a steam devil, technically. But the temperature was probably like -15, -10 at this time. We had very strong north winds coming down Cayuga Lake. And if you look at a map of Cayuga Lake, once we get to about Tacanic Park, the lake bends. And I think that bend in the lake funneled the air and created just a little bit of spin, and it was able to form this steam devil basically out over the lake. I've only ever seen one other picture off of Cayuga Lake of this, and so it's a very rare thing, and I'm sure it happens elsewhere in the world, but it's not something you usually see. So that's even a little bit different than a typical other type of water spout, but something that's very close to home. That's pretty cool.
Drew, I got a question for you.
Mhm.
The radar, what we see on our TV, our computer screens are pretty granular. Is there a way of getting more precise views on our computer screens than what we usually see?
Yeah, so all the radar data is coming from the National Weather Service. And then different vendors get that data and do different things with it. So it really depends on the source that you're getting the radar data from. Even on some of the programs I have, I can switch between different modes to see different things on the radar, and some of them are more coarse, some of them are more detailed. One app that I like, I don't remember if there is a free version. I pay like $10 a year for it. There's nothing going on around here right now. Let me see if I can find somewhere. I'll go look at Detroit's radar. See the snow that's coming in here later. And this is just a little band of snow, so it's not too much to see. But this is called Radar Scope, and a lot of storm chasers use it because it does kind of have that higher detail. And you can zoom in there. So that's one that I like to use on my phone. On my computer, like I said, I've got a program that displays all sorts of different weather things. So I use that one mostly on my computer. So yeah, people often will ask me like, well, my radar shows this and another one shows that's like, well, it's all the same data. It just depends on how they're, what filters they're running it through, what colors they put on it and all that.
I've got this one photograph I took one time up at it's on southern shore of Lake Ontario, and I see this looks like almost a rocket taking off, leaving a trail behind. And I would love to send it to you if you can, if it's anything at all. Doesn't
Yeah.
make any sense to me.
Yeah, go ahead. Yep, just Drew at
Okay, we'll
flxweather.com.
do, Drew. I gotta find it first. It's been a long time. I can
Yeah.
never explain it. It looks like, it looks like a steamer, a rocket or something, and it almost looks like one of those things you show on Hugo Lake there, but
Yeah.
I don't know if
Was
it is or not, but it's just curious.
yeah. Was it in the winter time?
No, it's actually summer.
Summer? Okay.
Yeah,
Very interesting. I look
yeah.
forward to
So
seeing that.
it may be absolutely nothing, maybe ghosts or something. I'll try and find it and send it off to you.
Great.
Thanks, Drew.
Yep.
I was amazed at the example you showed of the microburst happening right after the tornado, had microburst covering much bigger area, having much stronger winds.
Yeah.
Is that is the difference, the rotation is probably part of the difference, right? Is
Yeah.
it other things to think about right away about what the difference between those two things are?
Practically speaking, not really. You know, the microbursts tend to cover a larger area because it's kind of like this, big curtain of wind, whereas with the tornado, the spiral kind of consolidates itself, kind of like the figure skater pulling her arms in to go faster. Um, but yeah, it's mostly just
Hmm.
one's pushing winds this way and one's spiraling them. As far as what it actually means on the ground, that's about it.
The
And so
micro
that,
typically at the tail end of the storms.
not necessarily, no. It depends on where a location is relative to when the microburst hits, because microbursts start up in the cloud as like usually like this big pocket of rain cooled air, and it comes down and so it hits the ground and then it spreads outward. So you can get them on the tail end of a storm if the winds are kind of focused on the backside. But a lot of times when you know you'll know a thunderstorm is coming, you'll hear the thunder and you'll see the dark clouds coming, and then all of a sudden you'll get hit by this big gust of wind and it's not even raining yet. That's that outflow, that strong winds that can sometimes even race out ahead of the precipitation. So the microbursts can even outrun the rain sometimes. Usually it's probably a bit weaker by that time, but yeah, so it can be anywhere.
Yeah, we've had experience on Cuba Lake sailing. Sailing on Cuba Lake is unfortunate. You can't see what's coming from the west.
Yeah.
We were out there sailing and we saw some dark, actually like a roll cloud coming in, and at that point we couldn't do much of anything. But we got knocked down.
Oh man. Yeah. Yeah, they can come up very suddenly and when you're not quite ready for it. Okay, well, that takes us right to the top of the hour, so we did pretty much perfectly with timing. So thank you once again, everybody, for coming.
Well, thank you.
Definitely
That was
appreciate
really
it.
great.
Thank you. I always like talking about these things, so it's always a lot of fun.
I know you've got your website or your app out there. I've got it on my cell phone, so something I do watch. I have three different weathers radars and stations on there, so I kind of average the 3 or 4.
Yep. Yep, lots of people do that. I will note that the app for Android is outdated by about a year now. My developer's kind of gone missing. So if you have it on Android, it'll still work, but you can't go get it and download it new on Android. I believe the Apple version's still working okay, but that's just kind of what it is at this point. But yep, flxweather.com is where I post all my work. That's kind of the hub of everything. So you can always check it out there.
Thank you, Drew.
All right, thank
Thank
you. I
Thank you.
enjoy the rest of your day, and hopefully we'll get some warmer weather in here.
you. Bye-bye.
Take care.